Hello everyone, welcome to Infinity Learn by Sri Chaitanya. In this session, I will discuss AIIMS Physics paper Weekend Test 14. So let's start with the first question. A conducting sphere of radius r is charged to a potential of V volt. So potential will be kq upon r. So q will be Vr upon k. The electric field at a distance r, which is greater than capital R from the center of the sphere, would be. So electric field is given as kq upon r square, but the value of k is Vr upon k. So it is k into Vr upon k divided by r square. K cancels. So we have electric field as Vr upon small r square, and that is equals to option 3. Next is question number 2. A charged particle q is shot towards another charged particle q which is fixed with a speed v. It approaches q up to a closest distance r and then returns. If q were to given a speed 2v, the closest distance of approach would be. So when particles are at a closest different distance of approach, the velocity of the first particle will be 0. That means its kinetic energy half mv square is nothing but in the form of potential energy of the two charged particle system. So that is kq upon r. So r will be 2kq upon mv square. Now you can see that r is inversely proportional to v square. If you are increasing the value of speed by 2 times, closest distance of approach will decrease by 1 by 4 times. So new closest distance of approach will be option 4, r by 4. Question 3. ABC are the 3 points in a uniform electric field. The electric potential is. So you can see that electric field is directed towards right. Okay, and we know that electric field is always in the direction of decreasing potential. So potential at A must be minimum, then C, then at B. So maximum potential will be at B. So correct answer is option 4. Question number 4. Mark the correct statement where V is electric potential and E is electrostatic field. First is, if E is 0 at a certain point, then V should be 0 at that point. It is not necessarily true because E is equals to minus dV upon dx, right? So V can be constant, right? If E is 0, V can be constant. So this is not true. If E is not 0 at a certain point, then V should not be 0 at that point. Again, not true. If V is 0 at a certain point, then E should be 0 at that point. Again, not true. And if V is 0 at a certain point, then E may or may not be 0, right? So this is true. So correct answer is option 4. Question number 5. A positively charged particle is released from rest in an uniform electric field. The electric potential energy of the charge is. So we have positively charged particle and it is released from rest, and as you can see that FDR minus FDR is equals to du for the conservative force field, right? So if particle is moving along the electric field, then force in dr will be in the same direction. So potential energy of the particle will decrease, right? So potential energy of the positively charged particle decreases because charge moves along the electric field, right? Because force vector and E vector will be parallel because it is what? A positively charged particle. So correct answer will be option 3. Next is question number 6. Point charges Q1, that is 2 microcoulomb, and Q2, which is minus 1 microcoulomb, are kept at x is equals to 0 and x is equals to 6 respectively. Electric potential will be 0 at the points. So let's say this is x is equals to 0. This is x is equals to 6, and I'm assuming that somewhere at x1 and x2 electric potential due to this configuration is 0. So this is 2 microcoulomb, this is minus 1 microcoulomb, right? So for this point electric potential to be 0, you can write net electric potential due to 2 and minus 1 microcoulomb as this distance will be x1. So this is k q upon x1, and this is minus 1 microcoulomb, so it will be plus k minus 1, and this distance will be 6 minus x1, right? So this is 6 minus x1 and it should be 0. So you can see that 2k upon x1 should be k upon 6 minus x1. K cancels. So we have 12 minus 2x1 is equals to x1. So x1 will be 4. So first value of x is 4. Now look at the second part. Let's say this is x2. At this point potential is 0. So this distance will be x2 minus 6 and this complete distance will be x2. So potential at x2 will be 2 into k divided by x2 plus k into minus 1 divided by x2 minus 6 is equals to 0. So it will be 2k upon x2 is equals to k upon x2 minus 6. K cancels. So we have 2x2 minus 12 is equals to x2 and x2 will be 12. So at x is equals to 4 and at x is equals to 12, you'll get electric potential 0. So correct answer is option 3. Question number 7. Choose the wrong statement. First is work done in moving a charge on equipotential surface is 0. That is true because on equipotential surface, potential will be constant. So delta V will be 0 and work done is Q delta V. So it will be 0. Electric lines of force are always normal to the equipotential surface. True. Right? Electric field lines enter or leaves the surface perpendicularly. Next is when two opposite charges are brought nearer, then electrostatic potential of the system increases. No, when two opposite charges are brought nearer, electrostatic potential energy is minus k q1 q2 upon r. So when r decreases, the potential energy also decreases, right? So it will be a wrong statement. So correct answer is option 3. Fourth is electric lines of force diverge at positive charge and converge towards negative charge. That is true. So correct option is option 3. Next is question number 8. We have three charges plus q. Sorry, not plus q. Only capital Q. Then plus small q and plus small q and are placed at the vertices of an equilateral triangle of side L as shown in the figure. If the net electrostatic energy of the system is 0, then Q is equal to. So because of this pair, electrostatic energy will be K Q upon L plus because of this pair, electrostatic energy will be K Q upon L plus because of this and this pair, electrostatic energy will be K Q upon L and it should be 0. So total energy should be 0. So you can write it as 2kq upon L plus kq square upon L and it should be 0. You can write it as 2q into kq upon L is equals to minus times kq square upon L. You can cancel kql from this term like this. So we are left with 2q is equals to minus small q and capital Q is minus q by 2, which is option 1. So correct answer is option 1. Next is question number 9. Find the flux through the cube if point charge q is placed at the corner of the cube. So this charge is shared by 8 such equal cubes, right? So through all the 8 cubes, total flux is q upon epsilon naught, right? So through one cube, it will be 1 upon 8 times total flux, which is 1 upon 8 times q upon epsilon naught. So correct answer is option 1. Question number 10. For a given surface, the Gauss's law is stated as enclosed integration E dot ds is equals to 0. From this, we can conclude that E is necessarily 0 on the surface. No. E is perpendicular to the surface at every point. No. The total flux through the surface is 0. Yes. E dot ds integration is 0. That means total flux through the surface will be 0. So correct answer is option 3. Question number 11. A hemispherical body is placed in a uniform electric field E. What is the flux linked with the curved surface if field is perpendicular to the base in figure? So basically electric field lines that are entering through this circular base is equal to electric field lines that are exiting from the curved surface. So flux entering through this surface will be E into A and that is equals to flux exiting through this surface. So this is incoming flux and this is outgoing flux. So if incoming flux is minus EA, then outgoing flux will be plus EA. Can we calculate incoming flux? Yes. So E is given as E and area is pi r square. So outgoing flux will be just positive of this value, that is equals to E into pi r square. So correct answer is option 3. Question number 12. An electric dipole is placed at an angle of 30 degree with the electric field intensity 2 into 10 power 5 Newton per coulomb. It experiences a torque of 4 Newton into meter. The charge on the dipole, if the dipole length is 2 centimeter, that is equals to 2 into 10 power minus 2 meter. So tau is given as PE sine theta. So you can find the value of P as 4 upon E, which is 2 into 10 power 5 sine 30 degree, which is 1 by 2. So P is 4 into 10 power minus 5, and that is equals to Q into L. So L is 2 into 10 power minus 2. If you solve this value, you'll get Q as 4 into 10 power minus 5 divided by 2 into 10 power minus 2, and that is equals to 2 millicoulomb. So correct answer is option 4. Question number 13. An electric dipole is kept in non-uniform electric field. It experiences, when the electric field is non-uniform, it can experience force as well as torque. So correct answer is option 1. Question number 14. A short dipole has a dipole moment of 16 into 10 power minus 9 coulomb into meter. The electric potential due to the dipole at a point at a distance 0.6 meter from the center of the dipole situated on the line making an angle of 60 degree with the dipole axis. So it is given as Kp cos theta upon r square. So it is 9 into 10 power 9. P is 16 into 10 power minus 9. Cos 60 degree is 1 by 2 divided by r square. So it is 0.6 into 0.6. So when you solve this one, it will be 8. This will cancel this. So we have 9 into 800 divided by 36. So this is 4, and we have the value of potential at this point as 200 volt. So correct answer is option 1. Next is question number 15. A particle is dropped from a height h. Okay. The de Broglie wavelength associated with the particle is proportional to. So we know that de Broglie wavelength is h upon p or h upon mv. When you drop a particle from a certain height, velocity acquired is under root 2gh. So you can write de Broglie wavelength as h upon m into under root 2gh. So by looking at this equation, you can say that lambda is inversely proportional to under root h, or it is directly proportional to h to the power minus 1 by 2. So correct answer is option 4. Question number 16. When a source of light is kept at 0.5 meter from a photocell, the cutoff voltage is found to be V0. If the distance of the source is doubled, then the cutoff voltage will be. So by changing the distance, intensity will change, but cutoff voltage is independent of the intensity. So that is why cutoff voltage will not change and it will remain as V0. So correct answer is option 2. Question number 17. Work function of lithium and copper are respectively 2.3 electron volt and 4 electron volts. So this is for lithium and this is for copper. Okay. Which one of the metal will be used for the photoelectric cell working with visible light? Okay. So lambda max for photoelectric effect can be 12375 divided by 2.3 for lithium. Okay. And it is approximately 5380 angstrom. For copper, lambda max will be 12375 divided by 4, and it is 3094 angstrom. So you can see that this wavelength of the light is not in the visible spectrum, it is in UV region, right? But this lies in the visible spectrum. So for visible, if you are working with visible light, you should use lithium, not copper. So correct answer is option 1. Question number 18. When a metallic surface is illuminated with the radiation of wavelength lambda, then stopping potential is V. If the same surface is illuminated with the radiation 2 lambda, stopping potential is V by 4. The threshold wavelength for the metallic surface is. So we can use this equation EVS is equals to hc upon lambda minus hc upon lambda naught, right? So for the first case, when the stopping potential is V and wavelength is lambda, it is EV is equals to hc upon lambda minus hc upon lambda naught. In the second case, it is EV upon 4 and that is equals to hc upon 2 lambda minus hc upon lambda naught. So you can write EV as 4 hc upon 2 lambda minus 4 hc upon lambda naught. Now you can equate this equation with this equation because both are equal to EV. So after equating this, you will get hc upon lambda minus hc upon lambda naught is equals to 2 hc upon lambda minus 4 hc upon lambda naught. So it will be, if you take this quantity over here, it will be, this is 4, right? So this will be hc upon 2 lambda. So this is 2, right? So it is 3 hc upon lambda naught is equals to hc upon lambda. Hc cancel. So we have lambda naught is equals to 3 lambda. So correct answer is option 2. Next question is question number 19. A surface irradiated with light of lambda is equals to 480 nanometer gives out electron with the maximum velocity v meter per second. The cutoff wavelength being 600 nanometer. The same surface would release electrons with the maximum velocity 2v meter per second if it is irradiated by a light of wavelength. So we need to find the wavelength for the second case. Let's say it is lambda dash, right? So we know that hc into 1 upon lambda minus 1 upon lambda naught is equals to what? Half m v square. For the second case, it will be hc into 1 upon lambda dash minus 1 upon lambda naught is equals to what? Half m into 2v whole square. If you divide these two equations, you will get hc cancel. So this is 1 upon lambda minus 1 upon lambda naught upon 1 upon lambda dash minus 1 upon lambda naught is equals to 1 by 4. So you have 4 upon lambda minus 4 upon lambda naught is equals to 1 by lambda dash minus 1 by lambda naught. So 1 by lambda dash will be 4 upon lambda minus 3 upon lambda naught. Right, so if you put the value of lambda as 480 nanometer and lambda naught as 600 nanometer, you'll get the value of lambda dash after solving this equation as 300 nanometer, which is option 4. Question number 20. An electron of mass m and a photon have same energy E. The ratio of de Broglie wavelength associated with them is. So lambda of electron is given as h upon p, which is equals to h upon under root 2 me. Similarly, lambda of photon is given as hc upon e. So lambda electron divided by lambda photon will be h upon under root 2 me divided by hc upon e. So after solving this one, you'll get h upon under root 2 me into E upon hc. H cancel. So we have 1 upon c under root E upon m into 2. Right. So correct answer is option 3. 1 upon c times under root E upon 2m. Next is question number 21. A particle of mass 3m at rest decays into two particles of masses m and 2m having non-zero velocities. The ratio of the de Broglie wavelengths of the particles is. So let's say momentum of the first is p1 and momentum of the second is p2. By conservation of momentum, p1 vector plus p2 vector should be 0 because initial momentum of the particle is 0. That means magnitude of p1 is equals to magnitude of p2 vector. Right. Now, de Broglie wavelength is h upon p, right? So h is constant. If p is same for both the particles, then lambda will be same, right? So lambda 1 upon lambda 2 will be 1, which is option 4. Next is question number 22. Light of frequency 1.5 times the threshold frequency is incident on photosensitive material. So threshold frequency is, let's say, mu naught, and frequency of the light is 1.5 mu naught. If the frequency is halved, that means new frequency is 1 by 2 times of 1.5 mu naught, which is equals to 0.75 mu naught. New frequency is less than the threshold frequency. If frequency of the incident light is less than threshold frequency, there will be no photoelectric current, right? So photocurrent will become 0. So correct answer is option 4. Next is question number 23. Which of the following figure represents the variation of particle momentum and the associated de Broglie wavelength? So lambda is h upon p. So lambda is inversely proportional to p. So correct relation will be shown by hyperbola, which is option 4. Next is question number 24. We have a light of wavelength 500 nanometer is incident on the metal with work function 2.23 electron volt. The de Broglie wavelength of the emitted electron is. So for that, we'll have to find the energy first. So it is 1240 divided by 500. So it will be 2.48 electron volt, right? And after that, we can use this equation. E is equals to W plus kinetic energy max, right? So from this one, kinetic energy maximum will be E minus W, which is equals to 2.48 minus 2.23. So this will be 0.25 electron volt, right? So after this, you can use this expression. Lambda should be greater than equal to 12.27 divided by under root V angstrom, right? So it should be 12.27 divided by under root V, which is 0.25 angstrom. If you solve this one, you'll get your answer as option 4, 2.45 into 10 power minus 9 meter, right? So correct answer is option 4. Next is question number 25. For a certain metal, the threshold frequency is mu naught. If light of frequency 2 mu naught is incident on it, the electron comes out with a maximum velocity of 4 into 10 power 6 meter per second. So in the first case, h into 2 mu naught is equals to h mu naught plus half m 4 into 10 power 6 meter per second square. This is 10 power 6, right? So it will be whole square, half mv square. For the second case, when the light frequency is 5 mu naught, so it is h into 5 mu naught is equals to h mu naught plus half mv square. Okay, so from first equation you can write this one, 2h mu naught is equals to h mu naught plus half mv square. So it is just h mu naught, that is equals to half m 4 into 10 power 6 whole square divided by second equation, which is 4h mu naught divided by over here half mv square, cancel, h mu naught cancel. So half of cancel also. So we have 4.6, 4 into, let me erase this thing, 4 into 10 power 6 divided by v whole square as 1 by 4. So 4 into 10 power 6 divided by v will be 1 by 2, and velocity in second case will be 8 into 10 power 6 meter per second, which is option 1. Next is question number 26. The curves 1, 2, 3 and 4 show the variation between the applied potential and the photoelectric current at two different intensities of light I1 greater than I2. In which figure is the correct variation shown? So, stopping potential V naught over here is independent of intensity. So, stopping potential will be same for all the values of intensities, and I is directly proportional to I. Okay. So, over here you can see that a photoelectric current is directly proportional to intensity. Okay, so in this case, if I1 is greater than I2, then I1 will be greater than I2. So in this graph you can see that for I1 intensity, which is more, photoelectric current is more. In this case, it is less. So correct answer is option 2. Question number 27. Davison-Germer experiment confirms de Broglie relation by converting electron into waves? No. Converting light into particles? No. Varying angle of incidence of an electromagnetic beam over a metal target and observing scattering pattern? No. Comparing theoretical value of the wavelength associated with the moving electron and practical value of wavelength measured by the observing diffraction pattern produced by electron? Yes, this was done, right? So correct answer is option 4. Next question is question number 28. A closed vessel A having volume V contains N2 at pressure P and temperature T. Another closed vessel B having the same volume V contains helium at the same pressure but temperature 2T. The ratio of the masses of N2 and Hg in the vessel A and B is. So for vessel A, we can write PV is equals to nRT. So PV will be same. N is the number of moles of N2. That is mass of N2 divided by 28 into RT. Similarly, for helium, it is PV is equals to nRT. So mass of helium divided by 4 into R into 2T, right? So this both expressions are equal to PV. So we can write mass of N2 divided by 28 into RT is equals to mass of helium divided by 4 into 2RT. RT cancel. So this will be mass of N2 divided by mass of helium is equals to 28 by 4 into 2. That is 14. So ratio of the mass of nitrogen to helium is equal to 14 is to 1, which is option 4. Next is question 29. Volume versus temperature graph for a given mass of an ideal gas are shown in the figure at two different values of constant pressure P1 and P2. What can be inferred about the relation between P1 and P2? So if you keep the temperature same for, let's say, 200 Kelvin, pressure for P1 line, volume is 10 and for P2 line, volume is 30. So volume V2 is greater than V1, right? And we know that PV is equals to nRT. I'm keeping temperature constant over here. That means pressure is inversely proportional to volume, right? If V2 is greater than V1, then P1 is greater than P2, right? So correct answer is option 1. Next is question number 30. At constant pressure, V1 and V2 are the volumes of a given mass at temperature 27 degrees Celsius and 54 degrees Celsius respectively. Then the ratio V1 to V2 will be. So we are keeping the pressure constant. So we can write V1 upon V2 is equals to T1 upon T2. Right. T1 is 27 plus 273, that is 300 Kelvin, and T2 is 27 273 plus 54 degrees Celsius. So this will be in Kelvin. So this is 7. This is 327 Kelvin, right? So V1 upon V2 will be T1 upon T2, that is 300 divided by 327, which is 100 divided by 109. So correct answer is option 1. Question number 31. The initial temperature of a gas is 200 Kelvin. The gas is contained in a closed rigid vessel. If the pressure of the gas is increased by 5%, calculate the increase in temperature of the gas. So this is T1. We are keeping volume constant. We have closed rigid vessel, right? So P1 upon P2 can be written as T1 upon T2. So T2 will be P2 upon P1 into T1, right? P2 is 5% more than P1. So let's say P1 is P. So P2 will be 105 by 100 P divided by P into T1 is 200, right? So T2 will be, this cancel. So we have 210 Kelvin, right? So change in temperature is T2 minus T1, that is 210 minus 200, so it is 10 Kelvin, and change in temperature in degrees Celsius is equal to change in temperature in Kelvin, so it is also equal to 10 degrees Celsius. So correct answer is option 4. Question number 32. In order to increase the volume of a gas to 3 times, so if initial volume is V, then final volume will be 3V. At a constant pressure, at 40 degrees Celsius, the final temperature should be. So initial temperature is 40 degrees Celsius. Let's say final temperature is T2. So we know that V1 upon V2 is equals to T1 upon T2. So T2 will be V2 upon V1 into T1. So it is 3V upon V into T1 is 40 plus 273 Kelvin. So this is 313 Kelvin, right? So this will be 939 Kelvin. If you convert it into degrees Celsius, it will be 939 into minus 273. So this is 6, this is 6 and this is 6. So 666 degrees Celsius will be the final temperature. So correct answer is option 1. Next is question number 33. If both the temperature and the volume of an ideal gas are doubled, the pressure is. So we know PV is equals to nRT. Let's say pressure is P. If we are keeping N and R same, of course, then volume is doubled and temperature is doubled. So it is this and this is 2T, right? So 2 will again cancel this one. So pressure will be again nRT upon V. Okay. So correct answer will be pressure remains constant. So it will remain unchanged and the correct answer is option 3. Question number 34. In Boyle's experiment, for a given gas at different temperatures, the graph between pressure and density are straight lines as shown in the figure. Then which of the following option is correct? So for a given density, let's say at D1 and volume V1, I'm keeping the volume same over here. You can see that pressure at T1 is more than pressure at T2, right? If this is P1 and this is P2, then pressure at temperature T1 is more than pressure at temperature T2, right? Now, if volume I'm keeping this particular volume for both the temperatures, then according to PV is equals to nRT, pressure is directly proportional to temperature over here, right? So if pressure is directly proportional to temperature for this particular value of volume and density, then for more pressure, temperature will be more. That means T1 will be greater than T2. So correct answer is option 1. Question number 35. 1 liter of helium gas at pressure 76 centimeter of Hg and temperature 27 degrees Celsius is heated till its pressure and volume are doubled. The final temperature attained by the gases. Okay. So we know PV is equals to nRT, right? If we are doubling pressure and volume, then it is 2P into 2V is equals to nRT dash. So it is 4PV is equals to nRT dash, but PV is nRT. So it is 4 into nRT is equals to nRT dash. NR cancel. So T dash will be 4 times the previous temperature. Previous temperature is 27 degrees Celsius, which is equal to 300 Kelvin. So it is T dash, which is 4 into 300, that is 1200 Kelvin. So it is 1200 minus 273, that is 927 degrees Celsius. So correct answer is option 2. Question number 36. If potential in volts in a region is expressed as 6xy minus y plus 2yz, the electric field at point 1, 1, 0 is. So let's find del V by del X first, keeping y and z constant. So it will be 6y only. Del V by del Y, keeping x and z constant. So it is 6x minus 1 plus 2z. And del V by del Z, keeping x and y constant. So it is 2y. Okay, put the value 1, 1, 0. So it is 6. It is 6 minus 1 plus 0, that is 5, and this is 2. Okay. Now electric field is given as minus of del V by del X I cap plus del V by del Y J cap plus del V by del Z K cap, right? So this will be minus of 6 I cap plus 5 J cap plus 2 K cap, and that is option 4. Next is question number 27. Two concentric spherical conducting shells of radii R and 2R carry charge Q and 2Q respectively. Okay, this is of radii R and this is of radii 2R and carry charge Q and 2Q respectively. Okay, the change in electric potential on the outer shell when the both are connected by a conducting wire is. So, when both are not connected, total potential on the outer shell will be KQ upon 2R because of the inner shell plus 2KQ upon 2R because of the outer shell charge. So, it is 3KQ upon 2R. Now, when we are connecting it with the conducting wire, charge will flow on the outer shell. So, total potential on the outer shell will be total charge K into total charge 3Q divided by 2R. So you can see that initial potential on the outer shell is equals to final potential on the outer shell. So change in electric potential will be 0. Question number 38. Three charges 2q, q and 2q minus q and minus q are placed at the vertices of an equilateral triangle at the center of the triangle. So if you look at the center, electric field due to this minus q will be towards itself, and because of plus 2q it will be away from it, right? So net effect will be not 0, है ना? Net effect will be not 0, so electric field is non-zero. But if you look at the potential, let's say this separation is r, this separation is r, and this separation is r. So total electric potential over here is minus kq divided by r, minus kq divided by r, and plus 2kq divided by r. So total summation is 0. So electric potential is 0, but electric field is non-zero. So correct answer is option 2. Question number 39. The variation of electric potential with distance r from a fixed point is shown in the figure. The electric field at r is equals to 5 centimeter is. So at r is equals to 5 centimeter, if you find the slope of this line from 4 to 6, then negative of the slope will give you what? Electric field. Okay, magnitude. Why? Because E is equals to minus dV by dr, and dV by dr is the slope of this line over here. So it is minus of slope is change in y, that is phi to 0. So it is 0 minus phi divided by change in x, that is 4 to 6. So it is 6 minus 4. So this is minus of minus phi upon 2, that is equals to 2.5 volt per centimeter. So correct answer is option 1. Next is question number 40. A point charge Q moves from point P to point S along the path PQRS, okay, in a uniform electric field. The work done by the field in the above process is given by the expression. Since this is your electric force is conservative force, so a work done will be path independent. It depends on the initial and final point, right? So initial point is A, B, 0. So that is AI cap plus BJ cap plus 0K cap. Final point is 0, 0, 0. So it is 0 I cap plus 0 J cap plus 0 K cap. So displacement vector S vector is what? 0 I cap plus 0 J cap plus 0 K cap minus AI cap plus BJ cap plus 0 K cap. So it is minus of AI cap plus BJ cap. Work done is force vector dot displacement vector. So force vector will be Q into E vector. E vector is along x-axis, right? So it is E I cap dot S vector is minus of AI cap plus BJ cap, right? So this will be QE minus A. So it is minus QAE, right? So correct answer is option 2. Question number 41. The electric field in a region of space is given by phi I cap plus 2 J cap Newton per coulomb. The electric flux due to this field through an area 2 meter per second, 2 meter square lying in xy plane in SI unit is. So if it is lying in xy plane, then its area vector will be parallel to x-axis. So you can assume that area vector is 2I cap, right? So electric flux phi is E dot A vector. So it is phi I cap plus 2J cap dot A vector, that is 2I cap. So this is 10. So correct answer is option 1. Question number 42. What is the electric flux linked with the closed surface? So flux linked is Q enclosed divided by epsilon naught. What is Q enclosed? 1.25 plus 7 plus 1 minus 0.4 divided by epsilon naught, which is 8.85 into 10 power minus 12. So total charge inside the closed surface is 8.85 divided by 8.85 into 10 power minus 12 will give you what? 10 power 12 Newton meter square per coulomb, right? So correct answer is option 2. Question number 43. We have three charges plus Q, plus 2Q, minus Q and minus Q are placed At the corners A, B and C of an equilateral triangle of side A as shown in the figure, the magnitude of dipole moment of this combination is. So we can break this plus 2q as plus q and plus q, right? So dipole moment because of this combination over here will be like this, negative to positive. This is P1 vector and the magnitude of P1 vector will be QA, charge into separation. Similarly, for this combination minus q and plus q, it will be P2 vector and its magnitude is again QA. So basically we have two equal magnitude dipole moments, but angle between them is 60 degree. So resultant dipole moment will be under root of P1 square plus P2 square plus 2P1 P2 cos 60 degree. So this is under root of QA square plus QA square plus 2 QA into QA cos 60 degree, which is 1 by 2. So this will be under root 3 QA. So correct answer is option 3. Next question is question number 44. The wrong statements among the following regarding photoelectric effect is: if photon and particle collision takes place in total energy is conserved, true. If in this process total momentum is also conserved, true. If a monochromatic radiation of a frequency more than the threshold frequency is used, then all electrons come out with same kinetic energy. No, this is wrong, because electron are coming out from different layers, so they'll come out with there might be possibility that they will come out with the different kinetic energy, right? So यहाँ पे over here the wrong statement is option 3. Next is question number 45. The maximum wavelength of a radiation that can produce photoelectric effect in a certain metal is 200 nanometer. So you can write lambda naught threshold frequency as 2000 angstrom. Okay, I'm converting nanometer into angstrom. And lambda is given as 100 nanometer, that is equals to 1000 angstrom. So the maximum kinetic energy acquired by the electron due to the radiations will be. So maximum kinetic energy over here is K max is equals to Hc 1 upon lambda minus 1 upon lambda naught, right? So you can write this thing like in angstrom like this. If you put the value of wavelength in angstrom, you can write this thing as Hc. The combined value of Hc in electron volt angstrom will be 12375 into 1 upon 1000 minus 1 upon 2000, and after solving this thing you'll get the kinetic energy maximum in electron volt as 6.2 electron volt. I hope this is clear, right? So correct answer is option 2. Next is question number 46. The electron is accelerated through a potential difference of 10,000 volt. Its de Broglie wavelength nearly is. So you can write lambda is equals to 12.27 divided by under root V angstrom for the electron. So it is 12.27 divided by under root of 10,000 angstrom, that is 10 power minus 10 meter, right? So after solving this one, you'll get lambda nearly as 12.27 into 10 power minus 12 meters. So correct answer will be option 3. Okay. Next is question number 47. So the figure shows the variation of a photocurrent with anode potential for a photosensitive surface for 3 different radiations: IA, IB and IC with the intensities, and FA, FB and FC with the frequencies for the curves A, B and C respectively. So you can see that for A and B, stopping potential is different, same, right? So FA is equals to FB, you can say that, and saturation current over here is directly proportional to intensity, so it is least for A, so IA will be less than IB. So correct answer over here is option 3. Next is question number 48. We have momentum of an electron and it is changed by delta P. The de Broglie wavelength associated with it changes by 0.50%. The initial length of the electron will be, initial momentum of the electron will be, right? So lambda is given as h upon p. If you are changing the de Broglie wavelength by 0.5%, the new wavelength will be lambda minus 0.5 divided by 100 into lambda and it is equals to h upon p plus, let's say, delta p. Change in momentum is delta p, right? So this will be 1 upon 200. So it is 199 lambda upon 100, and that is equals to h upon p plus delta p, right? So after cross multiplying, you can get p plus delta p as h upon lambda into 100 upon 199. Okay, but h upon lambda is p. So p plus delta p is equals to p times 100 into 100 divided by 199, right? So in this case, you'll get this is 200. Okay, this is 200. This is 200, right? So delta p will be p into 200 divided by 199 minus p, and that is equals to p upon 199, and that is equals to delta p. So p will be 199 times delta p, which is answer 3. I hope this is clear. Next is question number 49. A cylindrical tube of uniform cross-sectional area is fitted with two airtight frictionless pistons. The pistons are connected to each other by a metallic wire. Initially, the pressure of the gas is P naught and temperature is T naught. The atmospheric pressure is also P naught. The temperature of the gas is increased to 2 T naught. The tension in the wire will be. So basically, volume cannot change. So if you are increasing the temperature, pressure is directly proportional to temperature. If you are increasing the temperature to 2 times, then pressure will become 2 times. So if initial pressure inside the container is P naught, then final will be 2 P naught. Right. Now look at this piston. So it will experience forces because of tension. Next is pressure, 2 P naught inside the container. So pressure, because of that pressure, force in this direction, that is 2 P naught into A, and from outside, because of the atmospheric pressure, P naught into A. Now this piston is at rest, so net force T plus P naught should be balanced by 2 P naught into A. T plus P naught A should be balanced by 2 P naught into A. Why? Because net left force will be balanced by total right force. So tension will be P naught into A, and that is correct answer, option 2. Question number 50. 1 mole of a monoatomic gas is brought from state A to state B. The initial temperature at A is T naught. The temperature at B will be. So at A, you can write P naught V naught is equals to nR T naught, and at B, you can write 3 P naught into 3 V naught is equals to nRT. But 9 times P naught V naught is nRT over here. P naught V naught is nRT naught. So it is 9 into N RT naught is equals to nRT. NR cancel. So T is equals to 9T naught, which is option 4. I hope everything is clear so far. So that is it for today's session, guys, and all the best for the next paper. I'll see you again with the next solution. Thank you so much.